Right, thanks. So good evening, and I welcome you back to the evening session of today's lectures. So the lecture will be given by Professor Nir S from Weizmann Institute of Science, and he works as actually going through his website, and it's amazing areas where he's working. From collective cell migration to dynamic phases of molecular motors to active particles and membranes, and I believe he will talk about the last one. And his the title of the talk is Fluctuations and Pattern Formation in Active Membranes. So Neil, please, the stage is all yours.
Thank you, Anub. So it's a pleasure to be here, although it would have been much nicer to see you all in Bangalore. So is it okay? Everybody can see now the screen?
Yeah, perfectly fine.
Okay, so as I was discussing with the organizers, since originally this was supposed to be partially a school and a conference, I ended up preparing a talk which is partially pedagogical. So I hope it won't bore some of the experts in the audience. And I will try to cover in this talk two subjects that I was active in for a number of years now. The first one will be about how active forces that are non-equilibrium, that do not obey thermal fluctuations, that don't come from thermal fluctuations, when they're acting on the cell membrane and they appear as a sort of active noise, what kind of evidence do we have for such activity on membrane fluctuations? So these are random forces. And in the second part, I'll talk about active forces which are non-random. So they are directed forces. Their average on the membrane is non-zero. Say they are only pushing or only pulling the membrane inwards. And when they are non-uniform on the surface of the membrane, they can actually give rise to pattern formation. And we think that is a good way of modeling how the cytoskeleton of the cell is giving cells the variety of shapes that you see in organisms. So we start with the random forces that act on the cell membrane. So we think of the simplest problem and the simplest cell that exists, and that is the red blood cell. And that happened to be my first project when I sort of landed randomly into this world of biophysics, leaving quantum mechanics of my PhD and first postdoc behind. So this system has been known already from the 70s to exhibit flickering, which means that the membrane of this cell, it seems to be constantly fluctuating. But it took many years to realize that these fluctuations are not purely thermal fluctuations, but they also come from activity. And one of the hallmarks of that is if you see this movie that comes from this paper that is listed below, you see optically looking at a single cell and measuring the displacements field over the surface of the cell of the membrane, and you can see it quantified. And when the red blood cell is depleted from its energy store, which is in the form of the molecule ATP, you will see that the fluctuations become much smaller. And this will become much clearer now. You see that the whole shape of the cell has become much more condensed, and the whole fluctuation distribution is much narrower around zero. And you can see that the fluctuation spectrum of wave vectors has gone down significantly. So my interest in this, as I said, goes back to my first works in biophysics. So it's from 2004, and I list here a few important papers that we did theoretically on that general problem, I would say, over the years. So the last one listed here is 2011. And I'll just give you a flavor. This is now a little bit pedagogical, a flavor of the modeling, the theoretical modeling for the students among you. So we start off with this Helfrich free energy, which essentially says that the bending energy of a membrane comes from integrating the mean curvature over the entire surface of the membrane with this bending modulus, which is typically of the order of 10 to 100 kT. If we want to talk about deformations, let's start with small deformations, which can actually be quantified by a field H over initially flat membrane. And we can actually see that in that kind of modeling of the shape of the membrane, the local mean curvature is actually the second derivative of the height field. I apologize for using this letter kappa here again, but this kappa here stands for the curvature and not for the bending modulus, but it won't be repeated. This kappa here is from now on only the bending modulus. So if you write the total energy that is stored in these fluctuations, you get a bending term that is described by the first term here, and is the integral over this mean curvature, which is the second derivative squared. And we have another term that comes from just the surface tension, which is in fact a tension that comes from the fact that these thermal fluctuations store entropy in them. And by expanding and stretching out the membrane, you're actually ironing out and preventing and constraining the amplitude of these thermal fluctuations, and that costs energy. So with this energy, we can actually write it up to second order terms. And you can see that the first term, which gives you the bending energy, is dependent on the second derivative squared. And the tension part is dependent on the first derivative squared. And this first derivative squared simply comes from this expansion of the area element in terms of this extra area which is stored in these fluctuations, which change it from the flat state. If we then want to use that energy and calculate the forces that are involved with these thermal fluctuations and these bending and stretching of the membrane, we actually have to take the derivative, or in fact the variation of the total energy with respect to this small deformation. And doing a calculus of variation analysis, you can convince yourself that, and you can derive that this variation is given by these two terms. One is the fourth derivative now of the height field, and one is the second derivative of the height field. So the equation of motion for the membrane can be written in the following way. The rate of change of the height field is dependent on the forces, and the forces are the restoring forces that come from this variation of the free energy, which we just discussed in the previous slide, and any other forces that we want. And of course, this can stand for all the random forces, the noise forces that we will discuss, be it active forces or thermal forces. Now, why are we actually integrating over the entire surface, and what is this strange sign that is given here? We're integrating over the entire surface of the membrane because, in fact, the displacement of the membrane in one place can be affected by forces that are moving the membrane in another location, and that is because of hydrodynamics. The membrane is embedded in a fluid, and whenever you need to move the membrane, you have to actually push the fluid in front of you, and a fluid behind you has to fill in the empty space. So this big O stands for this hydrodynamic friction, which can be calculated analytically for simple geometries such as a flat membrane or a cylindrical membrane, but is of course more complicated and is not analytically solvable for a general shape. If you're wondering why we left the energy functional behind and we are treating now only forces and equations of motion, the reason is because we want to add non-equilibrium forces. And non-equilibrium forces mean that we have to give up on using thermodynamic relations, because we are actually now using force. We will be introducing forces that are not coming from conserving Hamiltonians or energies, but in fact are coming from non-conserving processes, such as processes that consume ATP in the cell. Okay. So again, this is the equation of motion. We can Fourier transform it into a simpler form, and the Fourier transform of this hydrodynamic interaction is now written in terms of this inverse of the wave vector Q and eta, which is the viscosity, and it's called the Austin hydrodynamic interaction kernel. That's the name given for it. And you can see that now explicitly we can write the forces as being thermal forces, active forces, and any other forces that we want to add that act on the membrane. And now the treatment is in terms of the modes, which are enumerated by the wave vector Q, which, to remind you, is just 2 pi over the wavelength. So we start with thermal forces, and for thermal forces, we know that the average, the mean of the thermal force is 0. The thermal forces are random. They're pushing the membrane equally up and down. They are not overall giving you translation of the membrane. But the second moment of these thermal forces is non-zero, of course, and it's given by the temperature and the inverse of this Austin interaction kernel. This form of the thermal fluctuations obeys the fluctuation dissipation theorem, and we can convince ourselves of that. We can calculate the mean square fluctuations from the equation of motion. That's very straightforward, and it turns out to be this form for the thermal fluctuations. Don't forget that lambda q is the frequencies, the natural frequencies of the membrane at a wave vector q. And to calculate the response, we actually add an external drive, which is driven at a certain frequency, and we define the response function as the function that connects the deformation that you get per given external force driven at that particular frequency. So with this definition and the equation of motion, one can immediately calculate this Fourier transform of this response function. And now having the response function, and which is an imaginary function, as you can see from I here, and the mean square fluctuation, which we calculated here, which is a real function, we can actually plug them into this fluctuation dissipation relation, which actually says that the mean square fluctuation divided by twice the imaginary part of this response function is equal to the temperature, and that's exactly what these functions obey. So it's a constant, and that constant is just the temperature. By the way, you can also immediately use the equation, this mean square fluctuations that we calculated here, which was dependent on the frequency per each wave vector, and you can simply integrate that over the frequencies to get the amplitude of each wave vector of fluctuation, thermal fluctuation in the membrane, and you can see that it is only dependent on the temperature and the elastic moduli. It is not dependent on any dynamical variables such as viscosity. So what happens if we add active forces? So we will, for now, treat active forces that have their mean as 0, because we want to concentrate on random active forces. So active forces that will be assumed to be uniform on the membrane, but they are not giving any net force in any particular direction. So how are they different from thermal fluctuations? They are different in the second moment, which is now given by a particular force. So they are characterized by a force amplitude and by a typical time scale tau. So they are not a delta function in time. They are not a white noise. They are colored noise. And n is just the areal density of these motors on the membrane. We can consider direct force motors, just like is written here, so where the force is just immediately pushing on the membrane, or we can think of forces that are actually bending locally, and they have to couple to the local curvature, and since the local curvature is the second derivative times some spontaneous radius of curvature, we get this additional q to the 4 if we plug it into this f squared term over here. So from either direct motor activity or bending motor activity, we get these new expressions. And you can see that even though you might treat this thingy that sits here on top as some effective temperature, because the whole first part of this equation looks to be identical to the thermal case, you have this additional multiplication factor here, which comes from the fact that you have now a typical time scale for the active forces. And that is, of course, very different from what you get in a thermal case. We will assume that the thermal and active fluctuations are uncorrelated to simplify matters. The response function is unchanged by the fact that you're pushing with an active force or a thermal force, so that's the same as we calculated before. So we can now plug this. Oops. Can you hear me? Yeah.
Yes, we can hear you.
Okay. Okay. So we can plug this response and the fluctuations into a generalized fluctuation dissipation relation. So the thermal part just gives us the temperature, but the active part gives us a new term, which is shown here. And you can see that this term depends now on frequency. So this is not a constant. It depends on frequency. It depends on wave vector. It is certainly not a constant. And that's, of course, very different from the thermal case.
Nir, one window is popping up saying this. Please move this window.
Yeah, let me just reshare again. And let's start again because something got disconnected in my computer. Okay.
Yeah, now it's fine.
Okay, so let's resume the slideshow. Okay, so everything is fine now? Okay.
Yeah, perfect, yes.
So experimental verification took a long time. And this is just, again, maybe the older guys know that if we are theorists, we have to be patient with experimentalists, not jumping up and doing an impossibly complicated experiment just because we have a nice model to check. But for the younger students, I think this is a good lesson. So as you saw, the work, it was initiated in 2004, theoretically, and continued until 2011, more or less. But really striking verification, I would say, took longer. And this is from 2015. It's a collaboration with a group headed by Paco Monroy in Madrid. And you can see that they're looking optically at these red blood cells, and the fluctuations are quite large under normal conditions and become much smaller when you deplete of ATP. And of course, they become even smaller when you're basically fixating the cells with a fixative. But the overall amplitude, of course, is not enough because ATP modifies also the elastic moduli of the cell. So one could say, the devil's advocate could say, well, by removing ATP and seeing that there is a change, I don't know if it's a proof that there are active fluctuations in the red blood cell membrane. Maybe the ATP changes the elasticity. And as we saw, the thermal fluctuations are the temperature divided by the elastic moduli in essence. And if you make the elasticity larger, stiffer, then you reduce the amplitude. And in fact, this is also true. The ATP depletion also makes the cells stiffer. So how can you tell if it's purely that effect, or there is also active fluctuations which are now gone when ATP is depleted? So one has to look for a qualitative difference. And this actually was nicely shown in this work, because when they looked at passive red blood cells, that red blood cells that had no ATP in them depleted, or most of the ATP depleted, they could measure the temporal fluctuation, the temporal correlations or fluctuations as function of time for different modes, different Q wave vectors of the cell. And you can see that under thermal fluctuations, we predict a single mode, which depends on the frequency, the natural frequency of the membrane for that particular mode. And actually that fits very well the experimental data. But when you look at a live red blood cell, you find that there is actually an additional bump that appears in the temporal fluctuations. Yes, there is a question? and this bump was actually mapped as function of the wave vector, and you can see that it's completely flat as function of the wave vector, so that its natural frequency seems to be a constant. It looks like a natural time scale that doesn't depend on the wave vector. And in fact, if you calculate from the simple model that I showed you before, this same temporal correlation, it should be time here, sorry, the temporal correlations as function of time, you find that there is a small additional contribution to the main mode, the mode that is also given thermally, but that is a very small contribution because this prefactor here is small for all wave vectors that are larger than some small value. But there is a new mode that appears, and that new mode is indeed at a wave, at a frequency which is completely constant, and is simply given by this tau, this natural time scale for this motor that we are presuming is active and giving external, additional active kicking to the red blood cell membrane. And from this expression and the thermal expression, we could actually calculate the ratio between the amplitudes of these two modes. And the calculated ratio is given by the red line, and the experimental data is given by the dots. And furthermore, we could also use that calculation to completely throw away the curvature type of local active forces, which only locally bend the membrane, because that predicts a completely different dependence of this ratio between the two modes, the thermal mode and this bump, this active mode, as function of the wave vector. So there are several things here which I think are interesting. First of all, there is a qualitatively new feature in the spectrum, and that feature fits nicely an active mode with a typical time scale. And furthermore, by comparing to this simple model, you can even tell if it's a direct type of active forces or a curvature type of active forces. We can also fit with exactly the same parameters that were fitted to the temporal correlations. We can also fit the power spectrum, and you can get nice fits between the active state and the completely passivated red blood cell, or the red blood cell which is partially passivated but seems to have some small activity remaining in it. The big problem with these calculations, although we're very excited, of course, is that all the mean square fluctuations that I showed you, and which are essentially what we are comparing to, are still dependent explicitly on the elastic moduli. You can see that, for example, here, where lambda q is the natural frequency of the membrane, and as you remember, that is dependent on kappa and sigma, just like is explicitly shown here in the thermal case, and that appears everywhere in these expressions as well as here. Sorry, not here, but here and here. So all these mean square fluctuations are still dependent on the elastic moduli, and as I said, the elastic moduli themselves are affected by the ATP depletion. So you don't have still a clean measure of only the activity without it being messed up with the ATP also affecting the elastic moduli themselves. So you don't know actually how can you tell the difference. So this had to wait for a really brave work, which was experimentally amazing and also theoretically very impressive, in a group in France, in Paris, headed by Timo Betz, and some names like Jean-François Joanny and Gerhard Gomper that I presume many of you know. The main student that did the theory was Hervé Tourlier, who is the first author, and Dmitry Fedosov was doing most of the simulations in Gomper's group. So it was really an experimental tour de force. So what Timo did is that he trapped a single red blood cell with four optical tweezers. So 4 beads are connected to a single cell, and they are held in an optical setup with 4 beams that are holding them. If you hold the cell with stiff beams or stiff traps on 3 sides and leave one of them soft, then you can measure the spontaneous fluctuations. You remember that gives us the power spectrum of the natural fluctuations. And now if you make that last trap also stiff, you can use it to apply an external force, and that external force you can actually now measure the response to that external force. So you can do on the same cell a measurement of the fluctuations and the measurement of the response function. As if you remember, we need the fluctuations and this imaginary part of the response function, which is the out of phase part, in order to plug into the fluctuation dissipation relation. And indeed, that's what he has done. And if you remember, the big thing, the big attraction is that the fluctuation dissipation relation, even the generalized one with the active forces, is independent of the elastic force, the elastic moduli. So when the ATP is depleted of the cells, you see that there is, I would say, almost perfect agreement between the direct measurement of the imaginary part, which is given by the black dots, and plugging in the fluctuations, which is denoted here by C of F. F is the frequency, into this fluctuation dissipation relation related to the frequency and the temperature. And you see that both expressions agree, which means that this is obeyed. But as soon as he went to normal cells or fresh cells, there was a significant deviation between these two calculations, which show that indeed they are not the same. Or in other words, the ratio between them is not simply just a constant T, but there is an additional term, and that additional term has at least the qualitative features exactly as the simple model that I described to you before predicts. First of all, at very high frequencies, this is essentially zero. So you go back to perfect agreement between the two expressions, and the fluctuation dissipation relation is obeyed. So depending on the frequency or the wave vector at which you are looking at your system, you could be completely oblivious to the fact that this is an active system, because it doesn't look like that at high frequencies. But at low frequencies, when this is small enough, then there is this contribution, which you see sort of kicks in when the frequency is below the inverse of this typical time. So you can read off the typical time from here to be something like 0.1 second. And of course, the amplitude depends on the density of these forces, these active forces, and the forces themselves. And it is saturating in the limit of zero frequency to some constant value, which we don't see here yet because we don't go to frequencies which might be low enough. So this, I would say, was the final nail in the coffin of the idea that the red blood cell fluctuations are purely all thermal. What are the motors in the red blood cell membrane? I actually didn't tell you any biology so far, and that's of course terrible. I won't tell you too much biology, but I'll tell you a little bit. So if you actually make a cartoon of how the red blood cell membrane looks like, it is a bilayer like you're used to from vesicles and other cells, and there is no three-dimensional cytoskeleton, so there's no biopolymers like actin or microtubules, or no motors that you are used to from regular cells like myosin, or at least they are not thought to be very active, although there's some new ideas that came out recently about that. But what we know there is existing there is this layer or a network of flexible molecules, which are denoted like springs here, or these filaments, blue filaments, which are shown here. And these are called spectrin, and they spontaneously form this almost perfect triangulated network that spans the entire inner surface of the red blood cell. Now, these molecular springs are constantly under stress when they are attached on both ends, and sometimes also additionally in the middle along the chain. They are entropically under stress because they would want to be in solution much more compact in order to be able to explore fully their deformation modes. Just like the membrane that we discussed originally, when stretching it, you're reducing its fluctuations, and that costs energy, and of course has to come with force. So they're under stress. And it turns out that ATP can come along and sporadically detach some of these structures that connect this network, either connecting disconnecting the individual strands or disconnecting, sorry, a group of them from the membrane. And that can release locally this stress, which is stored inside these springs. And if there is, now you could say, okay, but that releases only stress in the plane of the membrane. How will that actually kick the membrane up and down? Well, that could kick the membrane up and down if the membrane is in a curved region. So in a curved region, there is coupling between local stresses and normal deformations. And if you locally soften the stress, release the stress, you are causing some up or down, depending if you are now reconnecting the spectrin or disconnecting it. You can actually give these normal kicks. When Hervé actually...
can you have a short question?
Yes.
Yeah, so
this is Debashish. My question
Yes.
is that when you said the modes labeled by Q, did you mean these are plane wave modes or these are spherical harmonics or something else?
So that's a very good question. And indeed, when we, in this paper that I showed you in the beginning with Paco Monroy from Madrid, and also in this work with Timo and Hervé and Jean-François, of course, all the analysis was in terms of modes, spherical modes, because this is what you have to do when you're dealing with something which is quasi-spherical. Although, of course, beyond a certain wavelength, if beyond a certain frequency, if the frequency is high enough, it's indistinguishable between fluctuations of a flat membrane and fluctuations, I mean, short wavelength fluctuations of something which is very big and spherical. But for the large wavelength, you have to take into account the sphericity. And furthermore, because many of the optical methods in order to actually measure the fluctuation spectrum look only on the rim of the cell, you're actually also projecting all the different L modes onto just the M modes that you're actually observing, only the tangential modes that you're actually observing. And so you have to remember that what you're actually measuring is some integration of all the L numbers out of these L and M modes, and that actually changes by an integer these power laws that you get for the dependence of the frequency, the natural frequency on the wave vector. So that's a good question, and that has to be taken into account.
And these four tweezers that were put in, so those could have changed the nature of the spectrum, isn't it possible?
So that's true. It was worrying for a long time, and that's why I think what the experiment took many years to do. There was in this paper, in this Nature Physics paper, also a very amazing simulation that was carried out in Gerhard Gomper's group, where Dimitri actually simulated the triangulated network, not at the level of the spectrin. The simulation cannot go down to the level of a few nanometers over a cell of 8 microns, but at least it was able in this simulation to actually glue in the simulation such beads onto this red blood cell in silico, and actually see that it almost didn't affect the measurement. So it was actually checked only by testing it in a simulation, but it seems not to make a detrimental effect. It does modify, but not making a detrimental effect to the measurement.
Okay, thank you.
Now, so Hervé actually took this model with this spontaneous local softening of the stresses in the plane and converted them into normal motion depending on the local curvature. So that was a very complex calculation to do, but you could actually see that there was a very decent fit between this theory and the measurements. And that's already a theory which is much more detailed, of course, than the theory that I showed you in the beginning, which was just simply saying that there is a force and we don't care where it comes from. This is a much more detailed theory which actually says that this force actually comes from in-plane releases of pre-stresses at the level of the spectrins. So it aims to actually include the origin of these forces. So I think the conclusions of this part is that active noise is qualitatively different from thermal noise. We and many people also in some circumstances get away with calling it a higher effective temperature, and you'll see that notion in the literature, and I've used that notion, and I've actually even used it in calculations. So it's not a bad or a notion to use, but you have to be aware that it's not always the case that you can simply call the active noise an increase in the thermal noise. There, as we saw, it can actually give rise to new dynamical features like this new mode in the relaxation correlations that you see that was measured in the red blood cell, and of course a breakdown of the fluctuation dissipation theorem, which is the most striking feature. And I think also from this whole story that I told you that took something like over 10 years to complete, that first of all, simple models allow you actually to predict many features, even specific features for the red blood cell, but more, I would say, general properties of what to expect when you have active forces. Yes, sorry, somebody raised a hand.
Yeah, so I had a question. It might be very naive, but could there be a simplistic approach to calculate probably the form of the active noise from microscopics?
So it's a good question, and I think what Hervé did here, which was to take this level of modeling and implement it and arrive at this very nice fitting is a direction is a work in this direction. The problem is that if the active forces come from ion pumps or they come from different sources, you might have to go into a lot of details in order to be able to derive a lot of biochemical details in order to be able to derive how, let's say, a single ATP molecule ends up giving you this amount of force exerted on the membrane. And I think this has not been carried out in great detail because of the complexity of these systems.
Thank you.
But it's a worthwhile open frontier, I would say.
Yeah, thank you.
Nir, the same message is popping up once again.
Yeah, again, I don't know how do I get it? Is it? Can I just?
I think it's
how do I stop it? I don't know how to stop it. I'll have to stop share and start sharing again. Sorry, I don't know what is this. Why it started. Okay, that was quick. Okay,
right.
So we saw the conclusions, and now instead of dealing with uniform distribution of random forces, let's look at a membrane that has non-uniform distribution of non-random forces. Non-random forces meaning forces that actually give you a net push or a net pull in a particular direction. So they're not noise-like. They are not just fluctuating constantly, even if it's with some typical time scale. They are just not fluctuating. They are fluctuating in space. So you have a force in a certain point, and that point on the membrane can actually move around to a different location. So they are not uniform. They are really distributed non-uniformly. So the motivation for looking at such a model was actually looking at how cells get their shapes. So cells have a huge variety of shapes, and the reason they get these shapes and the reason they are not looking like vesicles, even though you can say that the red blood cell already has some nice biconcave shape and it's not just some random vesicle, it's still a rather spherical looking object. These are not, and the reason is that there is a cytoskeleton. Now, I will not tell you everything there is to know about the cytoskeleton because I don't know, and it's a subject of our course. But I would just say that what you see, for example, in these images are fluorescently labeled components of the cytoskeleton, and I think you can even see with your eyes bundles. These are not individual filaments; these are bundles of filaments, and the main filaments that exist inside the cell are those made out of a protein called actin and a protein called microtubules. And these are filaments that are stiff on the length scale of the cell. So they are actually able to form something similar, if you want, to your skeleton, which is stiff normally, and therefore gives you a shape. And therefore your hands and legs and everything stays in shape because it's built around a stiff core. And these stiff filaments are actually giving the cell its particular shape, and that's the key to giving these shapes. But unlike your bones, which are dynamic, but they are not, at least now, growing in any particular direction, many of these biopolymers are continuously polymerizing and depolymerizing. For example, actin is continuously polymerizing against the membrane or near the membrane, and thereby it's exerting a pressure on the membrane, and that pressure can actually push the membrane outwards. So we'll consider three components: the fluid membrane, which we already saw in the previous part, bending, of course, and effective tension and elasticity. And then there are the forces. So if you peel the membrane of a cell, not a red blood cell, but a real cell, a cell that has all the cytoskeleton and organelles inside of it, you can actually see this mass of filaments. And these are the actin filaments. And you can see that they are starting off near where the cell edge was and actually extending backwards. So they're continuously polymerizing against the membrane. And for example, this bundle of actin is especially efficient in polymerizing and therefore pushing against the membrane. So by polymerizing continuously next to the membrane, these actin polymers are able to exert a pushing force. So it's not anymore a random up and down equal force, it's a pushing force. In addition, you can have contractile forces from myosin motors, for example, that can grab two anti-parallel actin filaments and pull on them. These are myosin mini filaments, so myosin aggregates that have many heads, and you can see the effect of this. When a myosin is present, the membrane is being pulled back into the cell is growing from left to right, and when myosin is inhibited by a drug, there is a sudden release of that inwards motion, and actin polymerization can actually push the membrane outwards much more strongly. Of course, if the actin filaments are arranged specifically along a ring, and these myosins are also contracting along these filaments which are within this ring, this is much more effective than just pulling back on random filaments, and that is actually giving you the contractility that is necessary to drive cell division. So there are two forces you can exert. By polymerizing, you are pushing outwards, that was shown here, and by recruiting molecular motors, you can actually pull in. The third component that we will discuss is spontaneous curvature. Spontaneous curvature means that many of the proteins that are adsorbed on the membrane, inside the bilayer, or just on one side of the bilayer leaflets, induce local spontaneous curvature, local bending of the membrane. And that should actually not surprise you, because anything that adsorbs onto the membrane will break the symmetry of the bilayer and therefore induce some sort of curvature. It can be a very well-defined curvature or some undefined curvature. So with these three components, we can actually have a very interesting feedback that can lead to self-organization. So what you can have is that if a cell membrane deforms in some shape, and these deformations are driven by active forces, for example, of the cytoskeleton that are pushing, then if there are curved proteins that like a specific type of curvature, for example, the curvature that is in the tips of these bulges, then they will aggregate there. And of course, if these proteins themselves are those that recruit the cytoskeleton, you can actually complete a positive feedback. And I, not so long ago, 2 years ago, actually wrote a review of this line of work that we've been actually pushing already, as you'll see, for more than 10 years. So it all started with this collaboration with AJ, who is now in UC Merced, as I said, some 14 years ago. And we actually looked at this simplest kind of positive feedback that I was talking to you about. What happens if these proteins, which like this convex curvature, they like to be the tips of these protrusions, are not 100% uniform to begin with, just because of thermal fluctuations, for example. And since they're all pushing, because the actin is polymerizing behind them, then in the next instant of time, there will be larger bulge here where there was many of them, and sort of a trough where there's fewer of them, and that will actually induce them to flow even more strongly and aggregate even more strongly in these tips. And that is, of course, a positive feedback that could, under certain conditions, generate a spontaneous formation of some pattern. If they are oppositely curved, then this does not occur. So indeed, you can actually calculate, and I'll show you in a second, again, a short pedagogical part on how you calculate that. You can actually calculate that indeed there is what is called the Turing instability, or a finite wave vector instability, which means that if you calculate the rate of growth of an initial perturbation at some wave vector, you find that given the right conditions, there can be a shape of this form, which means that there is a region of wave vectors between 0 and some largest wave vector denoted here, or where the growth rate of these fluctuations is real and positive, which means that it actually grows exponentially. And whenever it is negative, as shown here for these very large wave vectors or very short wavelengths, it is negative, and therefore it means that all these modes are stable. They will not grow spontaneously, even if initiated, at least under linear stability analysis. And there is one particular wave vector here, which is that has the largest growth rate, and that, of course, is the one that you expect to find spontaneously if you start with some simulation of a random field of these proteins on even a linear contour and seeing how they evolve. Just to give you a flavor of the modeling, so unlike the free energy that we had before, which only had the curvature, simple curvature term, and the tension term, if you remember, now we have additional terms, because we have these curved membrane proteins which have some density phi, which is on the membrane. So first of all, because they are curved, they have some spontaneous curvature, which is denoted here by -1/r, so that if you take away from the membrane curvature the spontaneous curvature that they are inducing, you can actually see that the membrane curvature will not give you any energy contribution to the total energy if it perfectly fits the spontaneous curvature that these density of proteins actually would like to have at that particular location on the membrane. And in addition, you have to have all the entropy part, which comes from having a gas of these proteins on the membrane. So that's shown, it's an entropy, and that's shown by the fact that it's dependent on the temperature. A is just the typical lateral size of such a protein on the membrane. And in addition, you have interaction between these proteins. They could be slightly attractive to each other, so they have the tendency to aggregate, or not, depending on the size of this parameter J. So from this free energy, you can now again go back to your equation of motion that, as we did before, you do a variation to this free energy in order, for example, to calculate what is the equation of motion for the membrane deformation. But now there is an additional term here, because the active force is not in the form of an active noise, just like we had before, but it's in the form of a force that has all the time the same sign, in this case positive, so pushing upwards, but of course it's just a convention. And the F is a parameter which tells you how strong is the acting pushing force per given density of these proteins, and we remove the basal uniform density just to keep this system from flying off, so that there is some at the uniform state, it is not moving anywhere. There is sort of a balance of all the active forces. Now, since you have this additional field of these curved proteins on the membrane, you also have to calculate the equation of motion for this field. And the equation of motion for this field is nothing but the mass conservation equation. So what you have here is the diffusion coefficient, and this is simply just the divergence of the flow of the flux field in the membrane, and that flux is of course dependent also on the variation of the free energy. So if you take these equations of motion, you expand them up to linear order, Fourier transform, and you can actually carry out a linear stability analysis per mode, and that could give you, under certain conditions, these shapes for the dependence of the growth rate omega on the wave vector, and it can show you either an instability that has this form that extends all the way to large wave vectors, or it can have an instability that is limited to some range of wave vectors. You can see that the lower graph shows you parameter range where everything is stable, but it's on the verge of becoming unstable at one particular wave vector. So that's the flavor of the kind of modeling that we do. And just to tell you that at the time that we published this paper, there was actually no known convex protein that can recruit actin. And I even got personally shouted at by a biologist in one conference by saying that how can we calculate something that nobody has actually seen? But a year later, it was actually found that indeed there are these proteins that have this exact curvature that can actually give rise to this positive feedback. What was known at the time was that there are proteins with the opposite curvature, those that actually, if they are curved such that they actually prefer the troughs and not the tips. And those, if they are coupled to a pushing force, they don't give rise to any pattern formation. They only give rise to damped waves. So, of course, as theorists, you can consider that why should nature only have one curvature and not the other? And of course, it was found that nature does have all the kind of curvatures in its proteins. Don't think for a second that Shiro, Pekka, Stefano, and Giorgio found these proteins or looked for them because we had the theory. They were completely oblivious to the theory. But that's also a part of life that you have to accept when you do biophysics. It's still not the same culture as we're used to from physics itself. I mean, the connection between theory and experiments. More recent experiments found that indeed these proteins, this RSP53, for example, does sense curvature and can actually adsorb depending on the curvature of the membrane. And it was indeed shown that by aggregating and recruiting actin, it can actually give rise to this formation of these protrusions. And this cartoon can be exactly seen without any molecular details in our original paper with AJ. Just to tell you that, as I said, since spontaneous curvature can come up in many different forms, it was recently found, I mean, relatively recently, that these formins, which are another class of proteins which polymerize actin near a membrane, can also have spontaneous curvature. And not surprisingly, if they have spontaneous curvature and they can polymerize actin, lo and behold, they give rise to patterns such as protrusions. Another unlikely direction in which this theory actually found a nice manifestation is retrovirus budding from cells, HIV budding. So you can say, how is that related? Well, it's related in the following way. You can see that when cells are actually budding from an infected cell, they're actually building a coat. Each virus is building a coat of proteins on the cell membrane, bending it and forming a virion, which eventually will detach from the cell. But this virion has around it a part of the membrane of the cell. It's not a virus that completely explodes the cell and then just leaves on its own. It actually leaves by detaching a part of the membrane of the cell. And you could actually even see that there are actin filaments which seem to emanate from such budding sites. And indeed, if you manipulate genetically the virus such that it cannot actually now attach to actin, you find that it buds, but it only buds when the surface coverage of the infected cell by the coat proteins of the virus is a much higher density, and the individual budding events are much slower compared to the normal case where you almost don't find per image any budding sites, very few of them, because they occur very fast and they don't require a very high density of these proteins to cover the membrane. And you can explain it directly from the theory that I showed you before. You can actually plot as function of the actin protrusive force and the areal density of these viral proteins, which have exactly the kind of combination of properties that we want. They are curved, they are spontaneously curved just like we want, and they recruit actin polymerization. And why they are curved like that? Because they need to form a closed virion. And you can see that you can calculate from the black line the point on this phase diagram where the system becomes unstable, where there is a spontaneous growth of this aggregation of these curved proteins simultaneous with the budding. And the color just gives you the rate of growth of this unstable mode. And you can see that if you don't have actin protrusion, you need a much higher areal density of these curved proteins to cover the membrane before the membrane becomes unstable and aggregation turns on, as opposed to with a higher actin, with the ability to hijack the actin protrusion and actually begin to bud at a much lower areal density. And we presume that that's probably a good strategy for the virus, unfortunately for the patient, in order to begin to bud and infect other cells earlier and without needing to wait for a longer coverage of the infected cell. I don't have much time because it's almost an hour, so I'll just quickly tell you about a very recent work that's from last year that I did in collaboration with this group of nice people from Ljubljana. Maybe some of you know the names of Aleš and Veronica, who are in the business of membrane shapes for many years, and the members of their group. And what actually we did here was to go beyond linear stability analysis, which is essentially all that I showed you so far, and go into Monte Carlo simulations of a completely generalized triangulated vesicle, a triangulated membrane. So you can see an example, a snapshot of such a simulation here. And the energy functional that goes into this Monte Carlo simulation is also nothing new. People have seen that before. You have the bending energy with the two principal curvatures and the spontaneous curvature that might be or not be. Some binding energy between these red nodes, which denote that there is a protein in that location. And you can see from the shape of the membrane that these proteins are indeed considered naturally by us to be curved. So they have a finite spontaneous curvature C0. But that's all very nice. But in order to make it non-equilibrium, we make each of these locations where there are these proteins also a site of an outwards force to simulate actin polymerizing and pushing against the membrane. So you have this additional term that adds these active forces which are pushing the membrane outwards. So maybe very quickly, I'll just show you some nice results. You can actually start off with the passive system and look at the phase diagram as function of temperature and density. And of course, when you have high temperature and low density, it's just a gas. The insets show you the size distributions of the clusters. So almost all of them are just single proteins. There's almost no aggregations. From the model that I showed you about the viral budding, we can actually calculate a transition line for initiation of instability. And you can see that the critical temperature from that model, that viral budding model, shows you that there is a dependence on the force, just like I showed you in the phase diagram. And indeed, if you calculate from the simulation what is the line where the mean cluster size for the first time crosses 2, which might be like an initiation of budding, it actually follows quite nicely this predicted line from the model. You can actually do a more complex model where you calculate the spinodal, the instability, the thermodynamic instability of a system from a gas of monomers of these proteins to pearled aggregates where they form exactly these spheres that build on top of each other, and that gives you this red line, which is supposed to capture these transitions into large aggregates, but as you see, not perfectly. So what do you see in this passive system? The passive system is already interesting because you can see that indeed at high densities and low temperatures, you find these funny looking aggregates. They have been calculated in of course, simpler systems with cylindrical symmetry analytically before. You might actually say that it was already seen by a rather old paper from 1977 by Helfrich himself, but I wouldn't put my money on that. And many experiments actually show that you can get such pearled structures. And since this is a passive system, there's only one temperature which is relevant, and that's this transition temperature, which we calculated analytically. And you can show that indeed, if you take all the different data, for example, the mean cluster size versus temperature, and you normalize the temperature by this critical temperature, you get a nice collapse of all the data sets. For example, here, this is with different interaction energy W between the individual, the binding energies between the proteins, and everything collapses. So at least the passive system is well understood. Now what happens when you turn on activity, and I think this will be my last slide. First of all, we predict that as you turn on activity, you'll see a shift of this budding transition. You remember that was indeed the whole point of telling you why the HIV likes to hijack the actin. And indeed, again, if you plot the line of the mean cluster size equal to, it is shifted, and it's shifted roughly in accordance to what the analytic model predicts. But suddenly, below this red line, there's a new phase which is observed, which of course we didn't predict it from before, but as soon as we saw it, we said, of course, that's obvious. And what is this phase? Let me just zoom in on this phase. It's a pancake phase. And what happens here is actually very easy to understand. These curved proteins, they like high curvature, but they also induce a strong force. So small buds are in fact not very stable because there are forces that are going to expand small buds and rip them apart. But one configuration, which is in fact super stable for this system, is to have all of them along a rim. Now, I should have explicitly said it before. In this calculation, we don't conserve the volume of the vesicle. So we're conserving, by definition, the total area, but we allow it, as you see, to shrink in volume significantly without any energy cost. Now, of course, you could add osmotic pressure, and with high enough osmotic pressure, this transition, of course, will be completely inhibited. But if there is no strong osmotic pressure and water can flow out of the vesicle, you can actually have all these forces perfectly balancing each other and maintaining this structure super stably, as is shown here in this movie, which is of course not in real time, but in Monte Carlo time, but it just serves to show you that there is almost no spontaneous detachment of proteins that meander onto the flat regions, which are of course highly unsuitable for them because they are spontaneously curved and they like the high curvature of the rim. So I think with this, I'm out of time, so I'll just jump to the conclusions. There's, of course, many beautiful results that come out of such simulations. So I would say that first conclusion is that protrusive activity plus the convex curvature can drive faster budding. So just the budding events themselves can happen earlier or with lower coverage by these proteins, and that was shown to be significant for the HIV system. And above a critical cluster size, you can actually have these lamellipodia-looking structures. I'm calling them lamellipodia-looking because cells, when they are moving and migrating, they have in their leading edge very flat regions which are full of actin polymerizing against the membrane, which spontaneously have these flat-looking shapes, which are, of course, a big mystery, which people are interested in because they play a very important role in how cells adhere and spread on substrates and also how they migrate. And I didn't show you the results, but if I just keep activity, but I make these proteins completely flat so that they have zero spontaneous curvature, just like the blue membrane all around them, then you have another shape transition into these very dynamic long tethers, maybe looking like a philopodia, although we don't think so. but just to show you that it's the combination of curvature, spontaneous curvature, plus activity that gives you a very interesting range of shapes that are observed also in living cells. Yeah, thank you.
Thank you, Nir. So time for some questions.
Yeah.
Yeah, I have one question. Can I go ahead? Yeah, this is
Yeah.
Anirban from IIT Bombay.
Please.
Hi. So, did you say anything about why this convex curvature promotes polymerization? I mean, on the biology side, is there anything known?
So, yeah, well, I would recommend you to look up the papers by Shiro and Pekka and Giorgio. Where is it? Let me go back. Yeah. So you can see, for example, here that RSP53 is aggregating with other membrane components such as INA-VASP and CDC42, and together they form a complex that is then enabling the polymerization of the actin. So I think these objects which have these four circles, they are these INA-VASP which are thought to be sort of a processive capping protein. So it's a protein that is capping actin filaments, but it's processively capping them. So it's actually inducing polymerization. It's inducing a local region where monomers of actin can polymerize much more easily, because as you may know, the actin polymerization has an energy barrier to form spontaneously in the solution. It's actually not very easy to start, and that's good because you don't want the monomers to start polymerizing uncontrollably. So in fact, just by making a local chemical environment that is inducive to polymerization, the polymerization can actually initiate and continue. And you can see that they form complexes. So of course, in the model, we have a single entity that has both curvature and both induces forces. But in reality, this is not a single entity. It is a complex of proteins.
Okay.
Thanks. So we'll take a question from Vijay Krishnamurthy.
Yeah, hi Nir, this is Vijay from ICTS. So maybe you said this, maybe and I missed it. How is the simulation active? I mean, if you're doing Monte Carlo, you must be breaking detail balance somewhere.
Yeah, it's a good question. So look at this term in the Hamiltonian, which is the bottom one.
Yes.
It says that each point is actually lowering its energy if you move it towards its outwards normal. Now, by itself, that doesn't seem yet to break detailed balance. That's like an external force that's pulling from outwards. But the point is that this external force is constantly changing its location, because 1 minute this is the outwards normal, another minute it's this direction, the outwards normal. So each protein is in effect being pulled by sort of an external field, but that external field is not like just a gravity pulling everybody downwards, but it's constantly changing its location in space. So that means that if you have a constantly time-dependent external field, it's not an equilibrium system.
That's right. And what dictates the direction, the dynamics for those directions?
So the direction is just the local outwards normal. So by calculating the shape of the membrane, you calculate the local direction.
I see.
But it's a very, very good question, because we're actually now thinking of actually modifying that in order to make the local direction of the force dependent not just simply on the shape of the membrane, but dependent also on what the others are doing around it.
Right. But if it's just a local normal, I still can't see how it will be out of equilibrium, right? Because you could have some
just
local
because that normal changes constantly. It's not fixed in space.
Right. But the change is governed by the Hamiltonian.
Yes, but there is thermal fluctuations. So this protein is not in a fixed location. There's constantly a random flips of connectivity within this network to allow diffusion of these proteins.
Right.
So that constant, and of course the thermal fluctuations which bend this membrane. So the membrane is constantly bending and fluctuating thermally. So the source of these fluctuations is thermal, but you have an external force which is converting that into an out of equilibrium problem.
Okay, thanks.
So, Nir, we have another question from Sakuntala Chatterjee. She writes, can you comment on the relaxation towards these shaped structures? Starting from a flat membrane, what is the dynamics of this shape formation? For example, can I pull out some dynamical exponent?
You mean, for example, if you start with some shape and you end up with these pancake shapes?
Right.
So first of all, in order to really calculate correctly dynamics, you have to put in the hydrodynamics, and that doesn't exist here. So this is a membrane which is sort of in vacuum. There is no calculation here for the flows inside or outside. And I guess that if you really want to get a good measure of relaxations and frequencies and any temporal information, you would have to add that. And of course, that's a whole new ball game for the simulations. I think Gerhard Gomper has a nice scheme for doing that, but that was beyond what we did here. So I don't think this simulation here can answer that question. You can't follow it through the Monte Carlo steps, let's say, assuming maybe that the hydrodynamics is not the limiting factor, and what is limiting your dynamics is the translation of these proteins and how they are shifting within the membrane, which you might say that is sort of captured okay by these kind of simulations. Then yeah, I think that would be then more interesting and maybe revealing how you actually move from a vesicle that initially had a uniform random distribution of these objects to something where all the proteins are along the rim. I don't think we actually followed that in detail. We more, in that work, we actually more looked at the steady state shape. So I don't know how to answer that yet.
Yeah, so we have another question from Professor Debashish Chowdhury.
Nir, my question is somewhat like a comment. See, you know that many years ago, inspired by Mark Katz's paper, Can You Hear the Shape of a Drum? Burton Duplati wrote a paper, Can You Hear the Shape of a Membrane? But there, the fluctuations were all thermal fluctuations, and the membrane had its curvature elasticity. So now that, according to your experimental theory, the presence of non-thermal fluctuations are sort of accepted. So then the question would be that given the spectrum measured say from the same experiments, can one then predict the shape of the membrane?
That's a good question. Well, if you have the active fluctuations, I don't think that there is a general way to do that, because the active fluctuations, depend on detail. So, for example, if it's a direct force or a pinching force, like the curvature motors, you will get a different spectrum. So, I would say quantitatively, it depends on all the parameters that go into your active motors. Qualitatively, such as power laws, yeah, you can predict specific power laws. If by power laws, like spectra from power laws, you mean by as hearing, then you can then yes. For example, if I go back to the first part. Yeah. So for example, in this part, for example. So at high frequencies, you're dominated by the thermal fluctuations, and you know how their spectrum looks like as function of the frequency. So if there is a regime where you are activity dominated, so you're not at high frequencies, and you are still able to measure over, significant range, so that you can define a meaningful power law, so that you're not dependent on any particular numbers of prefactors, but you can actually pull out from the experiment something clean like a power law, which I don't think this experiment allows you to. Then yes, then you could say that you can hear the type of active noise that you have in the system. But you see that it's a very tricky thing to pull out from the experiment.
No, my question is probably slightly different. See, as you said, my earlier question was regarding, what kind of shape you assume, because the spectrum will depend on the shape. So whether it is spherical, plane, or what. So in this case, suppose, you don't know the detailed shape of the membrane that was used by the experiment, but they know the spectrum. From that shape, can you say that what must have been the shape, particularly because, see, it depends on the boundary condition also, right?
I've not seen anybody attempt that, and I guess the reason is that in experiments on living cells, the shapes are not so cleanly defined. I mean, even this biconcave shape, which is shown here in the cartoon, as you saw in the experiments, they don't look like that. If I go back to the experiments, yeah, I mean, you can see even here, yes, some of them are nicely defined, but what about these guys? So it actually goes back. Why does it go? Yeah, it actually goes back to looking at these fluctuations, right? You want to measure the fluctuations and tell me from this part what is the shape of this part.
Yeah.
And yeah, I don't think. Well, I think something along this line was tried by doing simulations, but nothing analytically. Because if you really want to take into account this shape of these cells, it becomes very difficult to calculate analytically. So I guess you must do it in simulations. As you can see, it's also changing its overall shape because of the changing stiffness as you are depleting the ATP.
Okay, so here it will.
But that's it's a good challenge. I don't know if anybody's answered that. Yeah.
Okay. Thank you.
Right. So if we do not have any more questions, so let us thank Nir for a fantastic talk. And
thank you all, guys. It's later for you than for me, so thank you for staying. And I hope by the time this pandemic is over, we can all meet in person, which is always much better for starting collaborations and discussing science, and also becoming friends, and really pushing collaborations, which I hope also this talk showed you that without collaborations, we are very limited in what we can do in science. So maybe next year, who knows?
Yep.
Yeah,
definitely. Yes.
Okay, guys.
Thank you, Dave. Thank you, Arnab. Thank you.
Thank you.
Thank you very much.
So we meet again tomorrow morning. Yeah.
Yeah. Okay. See you.
Thank you.